Hello everyone. Today I'm going to talk about the barrier to the small Polaron formation in metal peroxides. A Polaron is a quasi-particle used to understand the interactions between electrons and atoms in a solid. We all know that electrons move freely in metals. However, in some ionic or highly polar materials, electron can be trapped, and it will push its surrounding atoms away from their equilibrium position. We call this trapped electron or hole, together with its surrounding lattice distortion, a polaron. Polarons move slower than free electrons because it has to drag all the lattice distortions with it when it moves through these solids, so electron or hole mobility can be greatly decreased by the formation of polarons. Many energy materials suffered from polaron formation, so we would like to further understand the mechanisms of polaron formation in order to help improve the performance of many energy devices, and that's the motivation of our research. To look at the scope of our study, let me first demonstrate two different conducting mechanisms. For a free electron, it transports through conduction band, while for a localized electron, it transports through Polaronic hopping. And Polaron states are usually in the band gap, localized within one or a few atoms. Many research has already focused on the localized states, when the polaron has already formed and then moved by Polaronic hopping. The transition from when a free electron is at conduction band minimum and until the electron is finally localized at the Polaron state. Some earlier work has studied this transition process, such as Mott and Stoneham proposed a model to explain this Polaron formation mechanisms. Here, y-axis represents energy and x-axis represents distortion of atoms. We could see that a polaron forms because the energy gets lowered compared with free electron configuration. In this case, there is also an activation barrier separating these two states. Mott and Stoneham separated the polaron formation energy into two parts. One is lattice penalty, and another is electronic relaxation. The stabilization energy of the small polaron is a balance between these two energy terms. The lattice energy penalty is due to lattice distortion when forming a polaron. It is like when you stretch a spring away from its equilibrium position, and the potential energy of the spring goes up. So the lattice energy goes up immediately once there are distortions. But only a finite value of distortion will it be able to trap an extra electron. They think because in 3 dimensions, a potential well's radius and depth has to reach a certain value in order to trap a carrier, so only after a finite value of distortion, the electronic energy will be lowered. Mott and Stoneham used this finite quantum well to explain this delay. We would like to apply first principle method to understand more of this delay, so as a barrier in the perspective of the electronic structure of materials. In this project, we have looked at 4 metal peroxides: lithium peroxide, sodium peroxide, potassium peroxide, and barium peroxide. These are the electronic structures of these 4 peroxides. We could see that the valence bands are all composed of oxygen orbitals. But if we look closely at the conduction band minimum, they are slightly different. In lithium peroxide, they are all from oxygen p orbitals denoted in red, while in sodium peroxide and potassium peroxide, the contribution of CBM is a mixture between oxygen atoms and metal atoms. So they are purplish. In barium peroxide, the conduction band minimum is all from metal cations, denoted in blue. I will talk about how these differences in the conduction band minimum will impact upon the polaron formation very soon. Let's look at the crystal structure of lithium peroxide as an example. In lithium peroxide, oxygens are paired up and form peroxide anions, we can view these peroxide dimers embedded in the sea of lithium plus ions. When an extra electron is added to the lithium peroxide supercell, there are two possible configurations. One is free electron configuration, and another one is Polaron configuration. And when it is a free electron configuration, the extra electron is everywhere, and all the oxygen dimers in the supercell share the extra electron equally. The bond lengths of the oxygen dimer remain unchanged, denoted in this cartoon here. In contrast, if the symmetry of the lattice is broken, the injected electron will be localized on a single oxygen dimer, forming a small polaron, which is accompanied by a large lattice distortion. We are calculating the images between the free electron configuration and Polaron configuration, and we want to see the evolution between these two states. This is the energy curves during Polaron formation for the 4-metal peroxide. The barriers are quite different. Now the question becomes why lithium peroxide, sodium peroxide have almost no barrier, but potassium peroxide and barium peroxide have a large barrier. We notice that the barrier is very close to the starting point. Let's have a closer look near the barrier point. We did similar things as Mott and Stoneham. We separated the Polaron formation energy into two parts, lattice strain penalty and electronic relaxation. The lattice energy are about the same for 4-metal peroxide, but for electronic relaxation part, they have apparent differences. For materials have large Polaron formation barrier, it also have a large delay in electronic relaxation. So to understand the barrier, we have to find out where does this delay come from. Let's take a step back to look at how do we calculate these decomposed energy terms. The Polaron formation energy curve is just a linear interpolation between the free electron configuration and the Polaron configuration. We put the extra electron in the system, so we denote it as En plus 1. The lattice penalty energy curve is that we used exactly the same configurations as in the Polaron configuration, but without adding the extra electron in it, so we denote it as En. The electronic relaxation part is just the energy difference between total energy curve and the lattice strain penalty curve, so it's the difference between En plus 1 and En. This is a key step that leads to the understanding of the delay of the electronic relaxation. We use the generalized Kuhlmann theorem to connect the energy difference with a single particle energy level. The electronic relaxation energy here is just the energy difference term. While it is equal to a single particle energy level, the state to be filled with an extra electron, that is also the lowest unoccupied state in the electronic structure. So we will just track the energy state to see where does the electronic relaxation delay come from. This is the lower part of the conduction band of potassium peroxide. The gray area is from potassium S orbitals. Because the potassium atoms do not move a lot during the Polaron formation process, the states are almost fixed. And with the elongation of the oxygen dimer, the blue state from the oxygen atom starts showing up, but they still didn't reach to the bottom of the conduction band. The electronic relaxation is not lowered because the lowest unoccupied state doesn't change in the p-dot here. And this is the transition point. From this point, the blue states from the oxygen atoms become the bottommost of the conduction band. And because it becomes the bottommost of the conduction band at this bond length, when there's an extra electron, it will go to this oxygen dimer directly and localized. But before this point, the bottommost of the conduction band is mainly composed of potassium S orbitals, the gray area. So in that way, the electron energy will not be lowered. And there is a plateau in the electronic relaxation. And the electron energy level starts lowering down. And as the bond keeps stretching, the blue state keeps lowering and the electronic energy keeps dropping down. And this is our explanation of why there's a delay of electronic relaxation energy. With our research, we understand better why there's a delay, because only does the oxygen dimer stretches to a certain bond length and they contribute to the lowest unoccupied states where the electronic energy starts lowering down. Let's look again these two extreme cases. For lithium peroxide, the bottommost of the conduction band is mainly composed of oxygen p orbitals. With stretching of the oxygen dimer, the Polaron state moves down immediately. This cartoon here summarizes the results very well. If the conduction bands are all from oxygen p orbitals, there will be no delay because Polaron in the end also sits on the oxygen p orbitals. There will be a smooth transition from free electron state to the Polaron state. For barium peroxide, the bottom of the conduction band is barium d orbitals. The oxygen dimer has to stretch a longer distance in order to move down its oxygen p orbitals and starts localize an electron. This case is summarized in this cartoon here. The oxygen dimer has to stretch a longer distance to let it across the metal states to become the lowest unoccupied state in the band gap. So this metal state prevents the Polaron state moving down immediately because oxygen orbitals just hide behind this metal states, which cause a delay and larger barrier. To sum up, we applied generalized Kuhlmann theorem to connect the energy difference with a single particle energy level, which help us to see that the hybridization of the CBM play very important roles in Polaron formation barrier. That's the end of my talk today. You may also refer to our paper to have more information about it. Thank you very much for your attention.